capsule network is very recent compared to conventional neural network, but it has caught up a lot of attention very rapidly. Of course, this is work from Professor Hinton, and in the recent Turing Award interview in the CACM, Professor Hinton said the capsule network is the most exciting thing currently he's working on. So, you are in this tutorial to learn about this very interesting way to do the learning. And capsule network is more powerful and more sophisticated compared to CNN. So the main thing is that instead of having one neuron, we have a group of neuron, and group of neuron is called capsule network. So instead of just having one activation, we have, say, 16 activation or a 16-dimensional vector, which is the pose matrix, and we have one activation. The other important difference between capsule network and the convolutional neural network is there's a whole to port relationship. So the activation from previous layer to next layer they are not just passed the way they are passed in the standard CNN, but they depend on agreement. And there's a whole this routing process where their activation will depend on all other capsules. And that is, I think, very interesting. And it gets back to different parts of the objects and how they are related with different coordinate system, view invariance and eco invariance and so on, and inverse graphics, which is, getting into really details of the computer vision where we started. So we have exciting tutorial for you. So one thing, since this is so new and so involved, many people have problem understanding capsule networks and implementing. So this tutorial, our aim is to make it easier for you and give lots of details and references, resources which we have. So this is our agenda for today. So we will start with the presentation from Sarah Sabur from University of Toronto, and she has the two main papers in with Hinton and other collaborators about the capsule network. And it's only 2 years old. The paper is 2017, 2018. And then we will go through very quick survey by Yogesh, who will very quickly summarize the recent work in the capsule network, give you a flavor, what are the different things are being worked on, like what are the problems, like classification, localization, segmentation, and what are the different application of capsule network, and so on, and different variation of the routing algorithms. So after that, then we will have presentation from Kevin. He will talk about the video capsule network. So one thing is the capsule network are well known for memory hungry. So it's very difficult to fit in capsule network in a GPU. The initial paper was very small resolution, MNIST 28 by 28. But if you have large resolution, and of course if you have video, then it's a very challenging task to do this video capsule network. So Kevin will talk about his paper in NIPS last year on the video action localization and a couple of recent works he's working on. We will then have a break, short break. Before the break, we will have the question answer. So we won't have question answering during the presentation. So please, wait for this slot, then you can ask question answer. And after the break, when we come back, then we will have a presentation by Rodney. He will talk about the segmentation of medical imaging, the retinal images, lung images, especially the medical images are very large, and he has come up with a special way to fit in capsules and will show you that very few parameters using this implementation can get very good results compared to UNIT. Following that, then we will have a presentation from Tolga about the 3D capsule network, where using cloud of points to segment the 3D shapes and come up with different parts of the object. And he has some interpolation and also the part exchange, and you get actually starting from one object, you can come up with a very different, interesting object. And we'll end the tutorial by presentation by Marzia. She will talk about a little different way to do capsules. And capsules, in her case, are the subscale capsule network, where we still have a group of neurons, but for each class, we will have different subspace. And she will project the feature vector in different subspace of each classes and come up with interesting results. She had a paper in NIPS last year, and she has a follow-up work looking at the capsules, the subspace capsule in different layers. And the interesting thing about that is that there's no routing needed. And then after that, we will have last slot for question answering. Okay, so we will start with presentation from Sabur.
Hi everyone, my name is Sara Sabur. I apologize for not being present today due to the visa issues. I will be presenting an introductory talk in a series of talks on capsules and capsule networks. There is a QR code on all the slides for asking questions. Please feel free to post your questions during the talk. I will be answering posted questions after the talk. This will be approximately 40 minutes, and this is not a literature review. I will, however, review some motivations behind the research on capsules. I will introduce basic elements of capsule networks and discuss 3 variants of capsule networks. These basics will be useful to anyone interested in applying capsule networks to new domains with some modifications. We will have a survey of recent developments and capsule variants in the next sessions. Okay, let's begin. As you can see, QR codes are at the top right for asking questions. Let us start with a challenge. So this is for you, the audience, to solve. Take a moment to look at these 9 pictures. In 5 seconds, you are asked to draw all of them from memory as accurately as possible. So 1, 2, 3, 4, and 5. Now, patterns. Did anyone figure out any distinctive and shared patterns across all 9 examples? In fact, there are groups of points in the shapes of squares and triangles. On this slide, colors are used to highlight these patterns. By the end of this tutorial, we will learn about a system that can find such patterns. It can efficiently reconstruct the input, and it is unsupervised. Another challenge is occlusion. Occlusion is a computer vision challenge that is beyond simple pattern matching. Consider the following task that involves occlusion. Similar to MNIST, the task is digit classification. However, instead of 1, we have exactly 2 digits overlaid. The task is to predict the class of both digits. The ground truth labels are shown underneath each image. For example, the first image is a digit of 5 and a 9 overlaid on top of each other. Capsule networks perform significantly well on this task. The third challenge is viewpoint. The third computer challenge that we consider is generalizing to new viewpoints of the same object. Suppose we want to classify objects. At training time, we only get front view of the objects, but at test time, the image can be from any viewpoint. Capsule networks can also help us to generalize to new viewpoints. So, now let's ask a question. Suppose we call this picture a house. Then we can also call these two pictures houses, slightly transformed, but still the same general look. But if you separate the parts from the whole and mix them randomly, it is no longer a house. So the position and structure of lower level parts is important. In fact, we desire a system that is viewpoint equivariant at all levels. A system is viewpoint equivariant if any viewpoint change in the input results in a similar viewpoint variation in the output. And we want this to happen at all levels. So CNNs without a stride and pulling are translation equivariant, but not viewpoint equivariant. They replicate the computation over the grid of pixel positions equally. If you move the house around, for example, it will not hurt a CNN much. But if you change the viewpoint of the camera, CNNs do suffer. The question is, should we stick to CNNs and grid all degrees of freedom in the viewpoint as well? Or should we, for example, find new basis functions and replicate filters or computations in a new basis? A proposed solution is capsule networks. So let's drive capsule networks. As we discussed, in these pictures, viewpoint is varying. But what is staying constant? What is left of the house when we remove the viewpoint? The answer of computer graphics and older computer vision community is to go beyond pixel space into vector space. So put a coordinate frame on all the detectable objects, houses, roofs, walls, everything. The blue coordinate frame shown here is for the roofs, yellow for the walls, and green for the houses. Now look for the constant again. Can you see it? Yes. So take any roof in these pictures. Regardless of its coordinate frame, if you rotate it by 90 degrees and scale it, you can get the coordinate frame of the house. Basically, we can find the coordinate frame of the house from the roof from any viewpoint. We just need to learn the relation between coordinate frame of the house and the roof. So let's ask, what is a coordinate frame? A coordinate frame should encode information about the viewpoint, like rotation and scale. Suppose I ask you to put coordinate frames on this chalk and its parts. Here is one way you could do so. I'm arguing that the choice is arbitrary, but coordinate frame of parts have to be consistent with each other. The coordinate frames are multidimensional. A vector or a matrix is a proper representation mathematically for coordinate frames. What we need to learn, however, is the relationship between two coordinate frames. We will represent these relationships using a single matrix. In a neural network, usually we only carry around the information about the existence of a pattern. In addition to that, we want to carry how it exists now. So we introduce a new concept, capsules. From now on, we will call a group of neurons representing whether an entity exists and how it exists a capsule. A capsule can be just 6 neurons, which we will represent using a single vector. Or it can be 16 neurons formed as a 4x4 matrix. The point, or any representation, essentially. The point is that any group of semantically meaningful neurons is called a capsule from now on. So we have figured out the constant and variable parts of a house representation. In the house example, we will represent a roof using a capsule and a house using another capsule. And we will learn to find the transformation from the roof capsule to the house capsule. This transformation will give us how the house exists. But how can we detect objects? Is any roof a house? No, a house needs walls. So a house exists if it has both roof and walls. Suppose we know how to transform a roof capsule to a house capsule. We also know how to transform a wall capsule to a house capsule. But the house capsule should only be active if and only if the prediction matches between the roof capsule and the wall capsule. In other words, roof capsule and the wall capsule should agree on their prediction for the house, and then the house exists. So let's take a look at what do we mean by this agreement. Consider a digit classification task like MNIST and a model with the following architecture. The model consists of 3 layers. The first capsule layer consists of 7 part capsules. Example parts in a digit are shown in the bottom. Each of these capsules will find their individual coordinate frames. First layer capsules are connected to the second layer capsules consisting of 5 capsules. Second layer capsules will be responsible for detecting higher level conceptual parts, such as the image on the right. For example, these are 3 examples of what conceptual parts they can represent. And we carry the coordinate frame information inside the capsule, not the actual part. Okay, now first layer capsules transform their coordinate frames and send 7 predictions to each mid-level capsule. That's what we have decided, to learn these transformations. So they transform their coordinate frames, send their transformations to the next level. Now we want to find agreement between each set of 7 predictions. Are these predictions agreeing? Are these the same? But not all predictions on the first layer belong to all mid-level capsules. For example, in this digit 3, some active capsules will belong to the red capsule, shown as the top part of the 3, and only to that part. Some of them belong to this other mid-level capsule, shown at the bottom left part of the 3. We only need agreement between parts that belong to a whole. This means in order to find an agreement, we need to also find a scene parse tree. In a parse tree for a scene, each capsule will get a parent and it will send its prediction only to its parent. A capsule with no child is turned off. Assigning parents is a layer-wise nonlinearity because parents compete with each other. This is a substantial difference between capsule networks and traditionally convolutional neural networks. In each layer of capsule network, groups of neurons compete with each other to find supporting parts. Like this one says, this is my part, the other one says, that's my part. And then within groups, neurons cooperate to explain the parts that they are assigned to them. This will be, in what follows, I will be discussing 3 approaches to finding agreements and assignments between capsules. This will be using dot products, expectation maximization, and mixture models. But before that, I will give a general architecture. So let's complete the architecture of capsule networks by connecting capsules to images and training the model. We connect the image to the first layer of capsules with a convolutional layer. Group the output of CNN into capsule neurons. Now, all the coordinate frames are transformed into the next capsule layer predictions. These transformations are the only trainable parameters between 2 capsule layers. Agreement is, given a set of capsule predictions, do these sets of coordinate frames agree with each other? We call this nonlinearity agreements and assignments. If the child prediction agree, the parent capsule gets activated. The parent capsule gets the agreement as its coordinate frame. I will explain this in further details later. Each last layer capsule is assigned to one class. The existence probability of that capsule is the probability of image be that class. A classification loss is used to train the network then. Okay, now let's dig into this agreement and assignment and child and parent and everything. The simplest method is using the cosine distance as the measure of agreement. Then set the norm of the coordinate frame to the existence probability of the capsule. Remember, for each capsule, we need an existence probability and a coordinate frame. This was introduced in a joint work with Nick and Jeff at NeurIPS 2017. So why does this work? Or how does it work? Let's illustrate each capsule as a vector. The orientation of the vector represents the coordinate frame. The length of the vector represents the probability of existence, just for the sake of visualizing and talking about them. Consider the following 2 cases. In the first case, the top half of the figure, the vectors have the same orientation. In the second case, the bottom half of the figure, the vectors do not align. What does the sum of these vectors look like? The length of the summed vector will be large if their orientation agree. To keep the lengths as proper probabilities, we renormalize the norm and squash them below 1. So summing the predictions and squashing gives the next capsule with an agreed orientation and a length below 1. Now that we have done with the agreement, we can refine it with doing some assignments. We use a ransack style refinement. Take these 5 capsules depicted as vectors, transform them into predictions for each of the 3 capsules in the next layer. Sum the predictions. This is the initial guess for our next layer capsules. Since orientation is our indicator of coordinate frame, compare the dot product of each prediction with the new capsule coordinate frame guess. For example, consider finding the parent of blue capsule. Take the dot product of all blue predictions with the summed capsules. The one with maximum dot product is the parent of the blue capsule, because the blue capsule is contributing most to this purple capsule. Remove the blue prediction for the other 2. All the 5 lower level capsules choose their parents based on the dot product and send predictions only to their parents. After assignment, recalculate the sum. Since now there is fewer outliers, the next layer capsules are boosted in compared to previous iteration. We call an agreement assignment step a routing iteration. This is a demo showing how after 10 routing iterations, capsules converge to a parent assignment. Here we show bottom level capsules with red circles, top level capsules with blue circles. At iteration 1, all red capsules send a prediction to all the blue capsules. Then they select soft parents based on their cosine similarity. Iteration 2 of the nonlinearity connections get sparser. In practice, using 3 iterations is enough, and we don't do 10 iterations. Consider the cluster task to illustrate the power of dynamic routing. This is a similar task to MNIST for classifying digits. But now there are 2 digits in each image overlaid. The images here show samples of the input images. The ground truth labels are also shown beneath them. Capsule networks have significantly better accuracy than the baseline CNNs in classifying these images, blah, blah. A capsule has coordinate frames in addition to the existence. That's the interesting part. We further investigate their performance by training a decoder on top of the coordinate frames. This is our decoder, for example. The decoder is an MLP to generate 28 by 28 images. On the bottom, we overlay the reconstructed images from the 2 most active capsules in red and green. So reconstruct from the 5, get a green 5, reconstruct from the 9, get a red 9, overlay them on top of each other, and the overlaps are yellow, shown as the first reconstruction. We see that if a pixel belongs to only 1 digit, it will only get reconstructed using that digit's coordinate frames. Let's take a closer look at these 2 examples. At the top left, we see an image of overlaid 9 and 5. At the top right, it's a 7 and a 1. The reconstructions at the bottom are from the 16-dimensional coordinate frames. Obviously, they are not perfect, but they're good. Looking at the corners, we see evidence of proper scene parsing. To explain the small tip at the corners, it does not thicken the other digit as it is customary with CNNs to minimize the reconstruction error. Since the nudge does not agree with the parts of other digit, it is not reconstructed from both coordinate frames. So in this case, it's only colored in red rather than a yellow. To evaluate CapsNet viewpoint generalization, after training on MNIST digits, we test them on affine transformed MNIST test digits. And capsules show significantly better viewpoint generalization than baseline CNNs. But using the norm as a measure of existence is problematic. If a coordinate frame is scaled, it should have a larger norm as well. So we need to represent existence separate from the capsule coordinate frame representation. Now we need to find agreement and assignment for this new capsule with separate existence. So far, the length of the coordinate frame was an indicator of existence. In the slides, we use arrows of different length to talk about capsules. Now, each capsule has a separate existence. So from now on, we refer to them as circles with different radiuses. The position of the circle shows the capsule coordinate frame. The radius shows their existence probability. How do we find agreement and assignment when existence is separate from the coordinate frame? Consider 10 low-level capsules shown on the left with different existence probabilities and coordinate frames. From the 10 capsules in the lower level, we want to figure out the next level 3 capsules on the right. First, we compute the predictions by transforming the coordinate frames. Note that these transformations are the only trainable parameters. They are learned by optimizing the classification laws at the end on the existence probability of the class capsules. Previously, we had cosine distance as the measure of agreement. Now the norm is part of the coordinate frame. So we use Euclidean distance as a measure of agreement. If the predicted coordinate frames agree with each other, then they form a cluster. Otherwise, they are scattered based on Euclidean distance. So we fit 3 Gaussians to find the agreements. We find the center of Gaussians by averaging the points. The black disks shows the Gaussians we get for each set. Their centers are marked with black squares. The math is similar to the maximization step in expectation maximization algorithm for fitting a mixture of Gaussians. Now, we take the center of the Gaussians as the coordinate frames of the new capsules. On the right, we show the 3 new capsules. To refine the capsules, we perform a parent assignment step. The math is similar to the expectation step in the EM algorithm. We choose parents based on which Gaussians explains which lower level capsule best. So for example, the red lower capsule has maximum probability under the pink Gaussian. It is best explained by the pink new capsule. So the red capsule chooses the pink capsule as its parent and send its prediction to only the pink capsule. Then we refit the Gaussians again with a maximization step. We recalculate the weighted average to find mean and standard deviation of the Gaussians. A capsule exists if its Gaussian is tight with several points assigned to it. So a Gaussian with large standard deviation or few children gets deactivated, like the new green capsule at the bottom. A tight capsule, like the new red one, is an active capsule though. Center of the clusters are coordinate frames of new capsules, and their standard deviation are a metric for existence. Let's take a look at how the assignments change in practice for real images during the routing. This experiment is on NORB dataset. Take the image on the right. We want to classify it into one of the 5 classes of animal, human, plane, truck, car. We are showing the number of predictions near the center of each of the 5 final layer capsules. At iteration 1, there are some predictions for all capsules near their centers. So all the 5 capsules are semi-active. At iteration 2, we reassign the lower level capsules based on their fit. Some of the class capsules lose support and some gain support and become tighter. After 3 EM iterations, the predictions settle correctly on track with a tight active capsule. Remember that this is a nonlinearity happening at inference training between each 2 capsule layers. This shows another example for a human image. Interestingly, after the first step, animal and human get boosted. This indicates that their part-whole relationships are similar, which makes sense. We also tested capsule networks on their ability to generalize to new viewpoints. We train on only 1/3 of available viewpoints in the NORB dataset. At test time, we ask it to extrapolate to new viewpoints. We compare capsule network results with a baseline CNN. Capsules have significantly lower test error in this task. So currently, at each step of training and inference, we are transforming and then running a loop to figure out centers. Can we do this without iterations? A new idea is to bypass the fitting and leave it to an MLP to figure out the capsule coordinate frames and perform the distance metric function, everything. Then the top capsules transform their coordinate frames and give predictions for the bottom capsule coordinate frames. The predictions are depicted via crosses in the lower capsule representation space on left. Take these predictions as the center of the Gaussians in a Gaussian mixture model. Each of the paired capsules picks the closest prediction as its parent. We learn the transformations and the MLP by optimizing the lower capsule coordinate frames under the predicted Gaussian mixture model. In addition to eliminating the loop, now this can be trained without supervision. It's a complete autoencoder, essentially. Let's take a look at the task that we started with. We color the points based on which parent they choose in the CapsNet. We see that the CapsNet finds the true underlying common parents in most cases. We compare our model with a baseline which has a decoder with several layers rather than single matrix transformation. All other aspects are kept the same. We compare the percentage of points that don't get grouped together. We see that the capsule autoencoder is significantly better at finding the underlying pattern without supervision. Assuming that viewpoint varies between images, capsule autoencoders can easily disentangle viewpoint from shape. During the past 40 minutes, we covered motivation for capsule research, introduced basic elements of a capsule network, talked about figuring out agreements and assignments. We have learned why finding agreement is advantageous to summing up evidence. Also, we have learned how to get smart sparsification and scene parsing via assigning parts to objects. We also gave 3 examples of practical techniques for accomplishing these functions. And that's about it. Thank you. Let's now take a look at the questions.
So if we see the timeline, then one of the first paper which talks about capsules, it came around in 2011, and then we have like another work which has similar ideas after 4 years in 2015. In 2017 actually there was a big breakthrough, and they came up with a routing algorithm which makes training easier in these capsule networks, and after that we have seen a great interest in the research community. So this will be the outline of my talk. I will start with a brief introduction covering the early works and video capsules. Then I will talk about the different variations in the routing algorithm we have. Then these capsule networks can be used in different modalities, so like visual, text, graphs, and I will briefly cover those as well. We have seen like use of these capsule networks in different problem domains, which are classification, segmentation, localization, and finally I will finish with a brief overview of different applications of capsule network. So these two are the very primitive works which talked about capsules, and they didn't have any routing, and that's why it was very difficult to train and expand these to like different problem domains. Then we have the foundational work which includes dynamic routing and EM routing, and then we have these video capsules which make these capsules scalable so that we can use those for high dimensional data as well. So in this initial notion of capsules, we represent a capsule as a vector of instantiation parameters, and each capsule is like supposed to represent a visual entity which is present in the input data. So the first variation we have, this was tried using autoencoders. This was the whole architecture which was proposed, and the idea here was if we have, let's say, our input image, then we will represent different visual entities present in this input image using these capsules. So in this case, we have 3 different capsules, and each capsule has 3 different instantiation parameters. Then the idea here was, can we use these instantiation parameters to predict some properties of the visual entity we have? So in this case, we are using these capsules to predict X and Y, the position of the visual entity in the input data. And along with this, we also have a probability which tells that whether this entity is present or not. To train such a network, the idea was we make some transformations to the input image. In this case, we have shifted this input image somewhat to the right. And to train this network, what we do is we try to reconstruct this transformed image. And the way it was done is we will pass these transformations, these delta x and delta y, which were used to transform this 2 in this image, and feed that as input to the capsules. And then whatever instantiation parameters are predicted by this capsule, we combine these two to actually do the reconstruction of this transformed image. So for the reconstruction, we have these generation units. So each of these transformations and the predictions are combined together and passed to the generation unit. And we have several generation units as we have these encoded capsules. We also use the probability, which is like telling us whether this entity is present or not, and combine with this to do the final reconstruction. And then when we have this, we can actually train these kind of networks end-to-end using backpropagation. So one interesting findings this network gave us is that, so this plot is showing the X value predicted by these capsules. So the Y is for the normal input image, and the X-axis is when we have transformed the image, like shifted whether by +3 or -3. So this green line here, it shows if we have transformed the image like with +3, and this blue line is with -3. So we plot these predicted X values for the original and the transformed image, and what we found is like these points exactly like along these lines, which validates that the predictions made by these capsules are actually very intuitive. The second work which talked about capsules was around similar lines. It has the idea of inverse graphics. There as well we have these autoencoders. Instead of fully connected networks, we have convolution networks here. So what we did is we have an input image, then we have convolution encoder. So instead of a latent representation, what we predict here is different properties of the entities we have in the input data. So these properties could be like pose, the lighting conditions, or the shape of the entity we have. And then these predicted, we can call these as capsules as well. So we can use these capsules along with the deconvolutional convolution neural network to do the reconstruction or to reconstruct an image which has some transformations based on these different properties. The interesting thing here is that again, this whole network can be trained like end-to-end using backpropagation, and when we try to modify some of these properties which is found in the input image, so for example, if you feed in this phase and we have a azimuth property here, if we change the azimuth, then we can actually reconstruct the phase with different variations here. So it shows that such properties which are visually there in the data, they can be actually captured or disentangled in the latent representation space. Then we have this dynamic trotting paper. I think Sarah will continue this in her slides, where the idea was we don't have to feed in any kind of transformations externally as we did in the first 2 papers. So all those transformations which we need from need to move from one capsule layer to another, those transformations can be learned inside the network itself. And then even if we have multiple entities in the input data, we can actually capture those 2 entities separately using the capsules. And if we try to reconstruct them, we can easily perform tasks such as segmentation. EM routing was along the similar lines where we try to learn those transformations. The only difference was in the routing algorithm, and I think Sarah is going to cover that in her talk. The big difference was in this EM routing paper, they tried to disentangle the pose and the activation information. So in the original dynamic routing, whatever instantiation parameters we have, we actually have to apply a squash function to actually limit it between 0 and 1 to do a proper training of the network. But if we do that squashing, it actually modifies the instantiation parameters as well. So it was really necessary to decouple those instantiation parameters with activation, whether their entity is present or not. So this was done in this EM routing, and this actually helped in a better training. So we have a different pose metrics, and along with that we have activation. So pose will just tell like different properties which are there in the visual entity, and activation will tell whether that entity is present in the input data or not. Then we have video capsules. The issue with using dynamic routing and EM routing for high dimensional data was the routing was very costly, and in video we have too many capsules and performing routing was not feasible. So we have scalability issue in high dimensional data. The reason is we will have too many capsules, and this will require like high memory consumption, which will make the routing slow. So we have this video capsule network where we have the idea of capsule pooling and sharing of the transformations which are used to move from one capsule layer to another. And these two topics will be covered by Kevin in a later session in more detail. So for routing, these were the original two works where we have dynamic routing, then we have EM routing version of that. So there are other variations as well. We have attention in routing. We can have like multiple modalities as input, and routing can be used to actually do some kind of filtering or attention, and we have some other variations as well. So this attention routing and multimodal routing, again we have a separate session for this, so we'll like talk in more detail in this. The whole idea of routing is we want to transform the lower level capsules or the parts which are present in the visual entity to a higher level capsule, which actually represents a holistic picture of whatever we have seen so far. So the main idea is to learn this parts to whole relationship. So for example, if we have these different parts of the face in the input data, and in one of the layer in our network, some of the capsules are actually representing these entities, then we want to transform from these low level entities to a higher level entity in the next layer. So for this transformation, we need to use routing, where the routing will tell like how to transform these entities to higher level entities. That's one thing. The other is not all the lower level capsules are used like to represent a higher level capsule. So we need to filter out the capsules which are actually not responsible for these higher level capsules. So that's why we need routing. And in routing, these transformations and these agreements are learned. So let me quickly talk about the differences between the two kind of basic routing techniques we have. So the basic idea is similar. We have some low level capsules. We want to learn these transformations which will move from this low level capsule to a higher level capsule. And along with these transformations, we also want to learn which of these capsules will actually activate the higher level capsule. So both of these algorithms are iterative. In dynamic routing, we have a squash function which actually tells whether this particular capsule is active or not. In EM, we have a different existential probability which tells whether this capsule is active or not. In dynamic routing, to find the agreement between lower level capsules, we have to actually transform those pose matrices to a linear vector and then perform cosine similarity. So this cosine similarity measure will tell whether lower level capsules are agreeing or not. In EM routing, it's quite different. The higher level capsules are actually represented using a Gaussian distribution, and whether the lower level capsules actually fall in that distribution or not, that will tell us whether we have to count those capsules towards the high level capsule or not. So apart from these two basic algorithms, we have some extensions as well which tries to actually improve the routing. There's one recent paper which talks about equivariance and invariance. So this is these two are like nice properties which are inherently there when we use capsules. So what they did is they actually enforced that these properties should be there when we perform routing. So they modify the routing algorithm to make sure that we definitely have these equivariance and invariance when we transform the lower level capsules to high level capsules. So for example, if In this case, we have an input image, and these are like lower level capsules. We perform routing to get the higher level capsules. So these are like the instantiation parameters. Here we are showing like the pose direction of the digit maybe, and then these blue plots are like how much this particular visual entity is activated or not. Now if we transform or rotate this particular image, then again we will have similar visual entities, and if it has equivariant property, then the pose matrix which we have, it should be like achievable by performing the same rotation or the same transformation on this pose data we have here. And again in the final layer of capsules as well, you can see that if you make the same amount of rotation to this pose vector, you can achieve this. So we do have this equivariant property. And regarding invariance, so even if we have rotated this digit, all the visual entities which are present in this image should be present in this as well. So the activations which is actually telling you whether this particular capsule is present or not, those should be consistent. And we can see here that for this particular entity, the activation is similar to this. So this enforces like there is invariance as well as equivariance when we perform routing. So they have some interesting results. For example, if you have a digit 3 and you try to rotate it, so this red arrow is showing like the pose vector they learned using the capsules. So it's actually pretty consistent across different variation in rotations, and it's moving along like wherever you rotate the input image to. One big issue with dynamic routing is that if you have too many capsules, it's very slow. And the reason is, when you perform routing, you have to use all the lower level capsules to actually compute votes for a higher level capsule. And if you have too many capsules, then that's actually a bottleneck, which makes the routing slow. So what they propose is they actually group these lower level capsules into different sets, which they call master and aid. And so now only these two sets will perform in different set of routings separately. So the transformations which we need, those will be like reduced exponentially. So they show that it's quite faster than the original dynamic routing algorithm. So far the work we have seen, we need routing to actually move from lower level capsules to higher level capsules. So routing will learn the transformation matrices as well as like the agreement. So we have another notion of capsule where we have like a group of activations, but moving from one layer to another, we don't need any routing. So this is like CapRoNet, last year NeurIPS paper. And the idea here is, instead of learning the transformation matrices or the agreement, we learn the class subspaces. And this is like enforced using by modifying the transformation matrices which we have. And once those subspaces are learned for each of the class capsules, then moving from one layer to another is quite simple. And in this case, X is if your capsule in a lower layer, we just get an orthonormal projection of that capsule into this subspace, and this is going to give you like your capsule for the next layer. And this is trying to explain this intuitively. So these red dots are like samples belonging to one class, the class for which we have the subspace. So you can see that like the activation or the intensity of all these capsules after the projection, they are actually quite high. And all these green dots are like samples from rest of the classes, which are not covered by this subspace. So in fact, this work will be later covered by Marzia in a session today. So with regard to modality, we have seen we use capsule networks for visual modality, we have used it for images, we have used it for videos. It can also be used for text. We can use it for graph structures as well, and we can also use it for 3D point clouds. And even if we have multiple modalities where we have combination of these three, we can still use these capsule networks. And there are some other works which we are not going to cover. So this 3D point cloud and this multimodal version, these will be covered in a later session today with more technical details. So the idea of using a capsule network for text, what we can do is we can use any textual embeddings. So let's say we have some input text. We can get some dimensional feature vector for each of the words in the sentence we have, and then we can use a set of convolutions on top of that to get the primary capsules. So again, these are just activation maps, and some transformations can give you the primary capsules. And then you can use the standard routing you have in the convolution way, and then the final this fully connected routing, which will give you the activation class for the input text. Again, this is for graphical capsules. The architecture is almost similar. The only difference is that given an input graphical model, first you will have to get embeddings for each of the nodes, and you have different ways to do that. You can use graphical neural networks, you can use graphical convolutional neural networks, and there are many other variations as well. And once you have these embeddings for each of the nodes, you can actually transform those to your primary capsules, and once you get your primary capsules in form of activations, you can use the same structure, perform routing on top of that, and perform classification. So this 3D point cloud will be covered later on, so I will not go into this. And multimodal will also be covered. So the idea here is we can have like two different modalities to perform some task or to solve a problem. For example, here we have an input video, and we have a textual description which talks about the actor which is present in this video, and we want to segment that actor in the video. So we'll have two different modalities. We can perform separate routing for the video modality, and then text we have seen like in the previous slide how we can get text capsules, and then we'll have this multimodal EM routing. We will talk about this in detail later today to get the filtered out capsules which can be used to do the localization. So most of the works which we have seen in Capsule, they require actually quite very less number of parameters as you compare with other methods which are using CNN, which are very deep. So there is one interesting work which is actually trying to make these capsule networks deeper. One issue with that is the routing will be like very difficult to perform. So their idea is they use a 3D convolution to perform routing, which is quite different than what we have seen so far. And they make use of these skip connections within the layer, which actually help them training the deeper networks. Another interesting idea they propose is to train these networks, we need a kind of regularization, and until now we were using the reconstruction laws for the regularization. And to do reconstruction, the idea was we have to perform masking of the class capsules, and the mask capsules are passed to a decoder to do the reconstruction. What they propose is instead of masking, they will just use the predicted class capsule and pass that to the decoder, and the finding is that it is actually a better way to regularize the capsule networks. So problem domains we have already seen, like classification tasks. Capsule networks are very effective for segmentation tasks as well as localization. So for classification, irrespective of the modality you have, you will have to get the primary capsules, and when you have those capsules, then on top of that you will have these convolution capsules which will be like feed forward using routing algorithm, and at the end you will have to perform a fully connected capsule routing here to get the class capsule. So this architecture will be like consistent across whatever problem you are trying to solve if you are doing classification. And this capsule network has also been found effective for segmentation tasks. This work we are going to go in more detail in a later session today. And again, for localization we have a separate session. There are different applications where this capsule network has already been used, and we'll cover like the relation extraction in the textual input. It can be used for adversary detection, brain tumor classification, and cancer classification, and there are many other works which we are not going to cover. So for relation extraction, given a text query, let's say you have different entities and you want to find a relation between these entities. Let's say for these two entities the relation is performer, and for these two it's occupation. So we can use capsule network for these because it can actually capture these entities separately, and it's easier to find the relation on top of that. So this is an interesting work where, similar to like the text classification network, they first like transform these input words in the sentence to some kind of embeddings. They also have the position here for each of the words. They have used this pyristimulator, but this should not be required. There is another work which actually has similar architecture, and even without using this LSTM layer to find the correlation, it works pretty well. And once you have the primary capsule layer, then your routing will help you find the relation between the entities present in the input text. This is another interesting application of capsule network. So let's say your input data has been like perturbed to change its class. Then what will happen is when you perform, when you use capsule network to do the encoding or to get the capsules from this input image, then the class which is like seeded into this image, that class will be highly active. And if you try to reconstruct the image using that class capsule, you will not get the visual input you are seeing. You will get like the target class which was actually seeded in there by an adversary. So the idea is you first encode the input which has some kind of attack present there, then you use the highly activated capsule to do the reconstruction, and based on what reconstruction you get, you can actually tell whether there is an adversary attack or not. So this is like one sample example. So all of these images were attacked using pan class. So if you use any classifier to classify these images, it will all of these will classify as pans. So in the capsule reconstruction, we observe that when you perform the reconstruction, we have some kind of notion here. So all of these will look like pans to you. So identifying adversarial attack is easier in these capsule networks. So we have some other applications like brain tumor classification, and the idea is simple here. Just take the images of or the scans of the tumors, perform standard convolutions, transform them to like primary capsules, perform routing, and you can classify like what category of tumor you have. You can have Decoder as a regularizer as well. So one interesting finding these guys have is the capsules they get for the tumor images, they can actually modify those capsules to actually do a reconstruction where they can control different things. For example, in this case, they are trying to modify the intensity in the brain components. They can also control the size of the tumor, and this is like on the parameter they are trying to elongate the tumor present in the image. So this is another application. Probably I will just skip this one because the architecture is almost similar. And the interesting finding is that if you use the learned capsules to actually separate different categories of cancer present in the input image, these are like quite distinct, whether the cancer is normal or is it benign or is invasive. Okay, so let me quickly go through the current challenges and the open problems we have in this area. So the benefits, as you will see today, these are very effective in performing tasks where we have segmentation or localization. The current issues are the routing algorithm. It's actually not very efficient right now. The optimization process takes a lot of time, and it's also memory extensive. So there is some interesting research which actually tries to solve this from hardware perspective, but I think there is a lot of scope of improvement in this direction. And another issue like we have is if we have too many class capsules, so the final layer in the capsule network is fully connected, so then we have memory issue with that. Again, the main intuition behind capsules is to learn parts to whole relationships using routing, and that's the reason capsule networks are very effective for segmentation or localization kind of problems. But it will be interesting to infer when we get the whole, can we get the parts from it? Or can we segment like different, let's say if we have a face, we can easily localize it, but can we also localize the smaller parts like the eyes or the ears from that? So that area has not been explored yet. We have seen different kind of interpretations using these capsules, but again, it's like very new right now. We don't have anything concrete where we can say that, yeah, these instantiation parameters like reflect different things. So we can say that, yeah, we can elongate the tumor or we can change the size of the tumor, but like more interesting properties. For example, if we have a video capture from certain viewpoint, then can we say that which viewpoint it was? So again, that kind of thing has not been done yet, and that will be really interesting. So this attention is inherent in capsules because when you perform routing, we are actually selecting some of the lower level capsules. We are not selecting them all to get the high level capsule. So it's already there, but still there is some scope, and we can learn from like the idea of self-attention and how we can improve this attention mechanism in capsule network in a more implicit way. Coordinate addition has been very helpful in training these networks, and we will see in a later session today how this is useful. But again, it's very hard to map those coordinates which are there embedded in the capsules back to the input data. So even we are getting like good localization, but those are like explicit localization. We cannot directly tell from the instantiation parameters of a capsule at which location in the input data this capsule belongs to, or where this is present. So there is some scope there as well. Some other problems are regarding multiple instances. So at the end, let's say we get some capsule which represents some type of class, let's say a dog. But if there are multiple dogs present, since we don't have that location embedding in that capsule, it's very hard to tell that there were multiple instances present in the input image. It can segment those objects when you perform localization, but again, the mapping from like which capsule belongs to which instance, that's not very clear right now. And this is another issue, like we have seen good performances on datasets like CIFAR and MNIST, but it's a long way to go, and on datasets which are like very large scale like ImageNet, Kinetics, AVA, we're still lagging behind like in terms of performance. So this is the link. I think everyone can access this from the CVPR website. We have like all the resources here, and we have put all the code which is like we have created, or all the papers we discussed today they have created. It has been shared there, so it will be a good resource for all of you. Thank you.
All right, so I'm going to present on video capsule networks. So capsule networks, as we've seen, they achieve very good results in classifying small images, so like data sets like MNIST and small node orb. But they've rarely been successfully applied on high dimensional data like large images and videos. The reason for this is that the capsule routing procedure is computationally costly, and deeper networks can't fit into memory. I'll briefly explain the computational cost of capsule routing. So if you think of convolutional capsule routing between two layers, you have CL represents the number of capsule types in the layer L, and CL+1 is the number of capsule types in the second layer, and KT, KX, and KY is the receptive field of the second layer capsules. So for each capsule in the second layer, it has to calculate this many votes, right? And each vote, it could be a 16-dimensional vector. So if you compute that at each pixel, the number of votes becomes very large, and it's very difficult to fit these into memory. So the number of votes becomes large if either the size of the layer is large, so if you have a large video input with a great number of pixels, or if the receptive field is large. I'll show this visually now. So first I'll go over conventional convolution, compare that to convolutional capsule layers. So given an input layer, we have some time dimension, some height, and some width, right, for videos, and we have some number of channels. We have a receptive field that is scanned across the image, and we apply some set of kernels. We do element-wise multiplication and then summation to get some scalar activations, and those are placed at that position in the output layer. This is conventional convolutions. Convolutional capsule layers are similar. So we have an input layer, but instead of different channels, we have different capsules. So we have CL capsule types. And each capsule is represented by a 16-dimensional pose matrix and an activation. Then we have a receptive field, once again, but instead of kernels, we have transformation matrices. So these transformation matrices try to get the lower level capsules prediction of the higher level capsules. These are multiplied by these lower level capsules to get our votes, and these votes are passed through a routing algorithm, in this case the EM routing algorithm, to get our output capsules, and those are placed in the output layer. So as you can see, this number of votes, since each one of these votes is a matrix, this number of votes is quite large. And if you try to fit a deep network, a capsule network into a GPU, you probably won't be able to. So we introduced two simplifications to this convolutional capsule routing. So the first is using the same transformation matrix for different capsules of the same type, and then capsule pooling. So if we go back to this figure, we can, instead of having a transformation matrix for each position of the receptive field, we can share transformation matrices between capsules of the same capsule type. Then we can multiply these transformation matrices with the receptive field and get our votes in that manner. But this doesn't really solve our issue because we still have the same number of votes. So for that reason, we introduced capsule pooling. So once we get a receptive field of capsules, we can pool those capsules into a single capsule for each capsule type. So now, when we apply the transformation matrices, we multiply them and we get our set of votes. We reduce the number of votes we have. So now the number of votes is no longer proportional to the receptive field size. It's only proportional to the number of capsules you want in both layers. So this allows us to fit deeper networks into memory and allows capsule networks to work on higher dimensional data. So I'll now talk about video capsule networks, specifically on three different tasks. So the first is action detection, where we want to localize and classify humans doing actions in videos. The second is multimodal task, where we want to segment an actor from a video based on some textual query. And the third is semi-supervised video object segmentation, where we have the first frame of the video segmented and we want to propagate that segmentation throughout the video. So I'll start with action detection. And this was a video capsule net. This was a NIPS 2018 paper. So modern action detection networks usually require multi-stage pipelines. So they have a region proposal network, and then those regions are passed through a secondary network that classify the regions and perform bounding box regressions. They often require optical flow, and they're rarely trained end-to-end. So ideally, we can create a capsule network that can that can localize and classify actions in a single end-to-end network. So that's what video capsule net is. The input to video capsule net is 8 frames of 112 by 112, so this is much larger than a simple 28 by 28 image. And the output is a localization map for each one of those 8 frames. So this is the overall architecture. I'll go over it briefly now. So it starts off with a set of 3D convolutions to obtain some feature maps. These feature maps have been downsampled to 28 by 28, but we still have the 8 frames. And then they're passed through a convolutional layer to get our first capsule layer with 32 capsule types. This first capsule layer is then followed by a convolutional capsule layer with that capsule routing to obtain 32 capsule types in ConCaps2. Then these capsules are fully connected to a set of class capsules. So these capsules represent the actions within the video, right? So if our data set has 24 actions, we have 24 class capsules which represent the different actions in the video. And because it's fully connected, we're going to lose some spatial information. So for that reason, we have a coordinate addition, which I'll briefly go over in a couple of slides. So once we have those class capsules, we want to localize that specific action in the video. To do that, we mask out all capsules except the ground truth capsule and pass it through a fully connected layer and a series of transpose convolutions to get our localization map. Here, skip connections are used to maintain that spatial temporal information, which is lost by the time it reaches the class capsules. So now I'll go over coordinate addition. So suppose we have a capsule at this position at time step 1 and at height and width 4 and 2. That capsule is going to create some votes for the class capsules. And this is, let's say this is the example vote matrix. If we want to encode that positional information, we could do it quite simply by just adding in the coordinates in the final 3 positions of the mode matrix, right? So the time coordinate is added in at this position, then the height coordinate, and then the width coordinate. And then when routing is performed using these votes, the class capsule will maintain this spatial temporal information. So this actually helps improve classification and localization results quite a bit. The next thing is capsule masking, which I mentioned. So capsule masking is useful for regularizing the capsule network. During training time, basically all classes except the ground truth class are masked out, right, replaced by zeros. And during testing time, when we don't have the ground truth class, we use the predicted class, so the class with the highest activation, and we use that for the localization. So video capsule net is trained end-to-end using 2 losses. The first is the classification loss. This is a margin loss. So basically what this tries to do is push the target activation, so the activation of the capsule corresponding to the ground truth class, to be higher than all other activations of the class capsules by some margin n. And then the segmentation loss is the standard binary cross entropy loss. And then the total loss is just a weighted sum of both of these. The segmentation loss is down-weighted because it could dominate the classification loss. So we want to make those losses similar. So the video capsule net achieves pretty good results on 3 different data sets, state-of-the-art results. So first is UCF Sports was the smallest data set we test on. It achieves 1% improvement in VMAP at 0.2 IOU threshold. For JHNV, we see a larger improvement, so about 15% VMAP at this threshold. And then for UCF 101, which is the largest one we test on, we can see a much larger improvement, so about 20% for VMAP and about 2% for FMAP. So here's some qualitative results. So the red bounding box is the human annotated ground truth, and then the blue is the network's output. So as you can see, if there's multiple humans, right, it correctly segments the one doing the correct action. In this case, if the human moves off screen, it's able to segment it quite well. And in these last 2, if there's quite a lot of motion, the network is still able to segment the human doing the action. So one thing you might want to know is how to interpret these class capsules. To do this, we ran some synthetic data set experiments. So this data set, we generate primitive shapes moving across a noisy background. And in this case, there will be 4 motion types. So there will be 4 class capsules, so linear motion, circular motion, some turn motion, and random motion. And these primitive shapes vary in different ways. So the shape, the color, the speed of these shapes would change throughout the video. So for example, these are 2 sample video clips. So a square moving to the right, and then a circle growing larger, right? These are 2 sample videos. So we can analyze the linear motion class capsule. We can give it different videos, but we change single properties of the video, so we could change the direction or the speed or the rotation and see how that changes the different dimensions of the class capsule. So these are the 16 dimensions of that class capsule, and this is varying the direction of the motion. So 0 would be right, left to right, and then pi would be right to left, right? And we have basically every direction here. And we can see that the capsule dimensions change quite predictably as the direction of the motion changes. And then notably, if we look at the final 3 dimensions, these are the ones that correspond with the coordinate addition. So the coordinate that corresponds with the height changes most when there's vertical motion, and the dimension that corresponds with the width changes most when there's horizontal motion. So you can see that this class capsule, this coordinate addition helps the class capsule maintain this spatial information. So in summary, I've shown you a 3D the generalization of capsule networks to 3D, showing you how capsule pooling can help fit deeper networks into memory, and I've shown you a capsule network that achieves state-of-the-art results on human action localization on 3 data sets. So now I'm going to move on to combining video and text in a capsule network using multimodal capsule routing. So as you saw in the survey earlier, capsules have been applied to several different modalities, images, videos, text, audio, 3D point clouds, but very little work has been done on merging these modalities. So one task in computer vision is actor-action segmentation from a sentence. So given a video, let's say this is our input video, and we want to segment an actor based on some textual query. So the dog is walking around the red cones, we would segment this dog here. And if we give it a different textual query, a woman in the green top standing on the left, we would segment this woman on the left. If we want to implement this in a capsule framework, you can create a set of capsules from the video and create a set of capsules from the text. And then you can use capsule routing to condition the video capsules based on the text capsules. And then you use these conditioned capsules to produce segmentations for all the frames in the video. Right, so here's a visual representation of that. So we have a video encoder, we get some video capsules, we do the same thing for the textual query, and then we pass that through some multimodal routing to get our routed capsules, and we get our output segmentation from these capsules. So if you're thinking of this in a capsule framework, both the video and the sentence will contain the same entity, right? So both the sentence and the video contain a woman, or both the video and the sentence contain a dog. So we can have a visual entity for the brown dog that's sitting, and we would have the same entities within the sentence. So sitting, brown, and dog, right? The same thing with the walking white dog and the woman in the green top. So these entities are present both in the sentence and the video, so that should also be represented by the capsules. So given an input video, we get our set of capsules in a grid, and then the different entities within the video should be represented at those positions. So this woman would be represented by the capsules at the position of the woman, the dog would be represented by these capsules, and this dog would be represented by these capsules. Similarly, a sentence, if we create a sentence capsules, right, the different objects within the sentence would be represented in these capsules. So now we can use routing by agreement to find a similarity between these capsules and the capsules at these 3 positions. So we have those capsules at those visual positions, the sentence capsules, and then when we do routing by agreement, we would find when these are routed, there would be no agreement. When these are routed, there would be no agreement. But then when the same entities are present in both, we would find agreement. So the output of the routing would be capsules with high activations. So I'll go over briefly the algorithm. So we have our video capsules represented by their poses and activations, our sentence capsules, and our transformation matrices. So this is the algorithm. First, we get a set of sentence capsule votes. Then for each position on the grid, we get the video capsules votes at the position. We can concatenate the activations and votes, and then pass that through the EM routing algorithm. So that tries to find agreement between the sentence and the video at each position spatially within the video. So this is a visual representation of that. So we have video capsules in a grid, we have the sentence capsules, and we get our set of actor capsules by performing this multimodal EM routing. I'll now go over the architecture of the network used to do this task. First, the video encoder. So the input is 4 frames of 224 by 224 resolution. It's passed through an i3D network to get some feature maps, and then these feature maps are transformed into a 20 by 20 grid of capsules with 8 capsule types. The textual query is passed through an encoder. So first, the words are changed into 300-dimensional embeddings using word2vec. Then 1D convolutions are passed over those embeddings to obtain a single feature vector after max pooling. and then a fully connected layer is applied to get 8 sentence capsules. So once we have the sentence and video capsules, we perform multimodal EM routing using the algorithm I stated before. And this produces a set of actor capsules. For the data set we're working with, which is A to D, there's 7 actor classes and 1 background class. So we decide to use 8 capsule types in this for the actor capsules. This is not really necessary, but we find that adding this class to capsule correspondence really helps in the training of capsule networks. So similarly to the video capsule net, we use capsule masking, which lets us have this class-based segmentation. And that improves our results. So these masked capsules are then sent to an upsampling network. It consists of 5 convolutional transpose layers, and the output is segmentation for each frame that was given to the network. This network is trained end-to-end. It only really requires a segmentation loss, which is the binary cross-entropy loss. But if we add in a classification loss, that extra supervision helps the capsules learn more meaningful representations. And for that, we use the margin loss I mentioned earlier. And the final loss is a weighted sum of both of these losses. So we perform experiments in several data sets, but the largest of which was A to D. And it achieves state-of-the-art results across the board when compared to other methods. Notably, it performs much better at higher overlap thresholds, which means that the segmentations produced by the network are much better than standard convolutional networks. Here are some qualitative results. So given this video, we have 2 sentences. A person is walking backwards while being followed by a dog, and a black dog is crawling. So as you can see, the person and the dog are both segmented quite well, right? The gap between the person's legs is segmented, and then the dog's tail is finely segmented. So this is our network trained on segmentations. If we wanted to train it on bounding box annotations, we can see the second row here. So the segmentations are not as fine because it's trained on bounding boxes. But even with that those noisy annotations, our network is able to segment quite well. And here's another example with 3 actors. So a baby and 2 dogs. And even when the actors are quite small, the capsule network is able to localize it quite well. And here's some video examples. So a parrot jumping, baby climbing up the stairs. So here's an example with 2 actors, the baby and the ball. And here's an example with the car bouncing and a person filming. So even when there's multiple people, it only selects the person filming. So you can see that the capsules are learning that representation of the sentences and corresponding it to the video. So I've shown you a new multimodal capsule routing method, an end-to-end capsule network for video segmentation from a sentence, and it achieves state-of-the-art results on A to D. So the final part I'll talk about now, the final capsule network I'll talk about is one for semi-supervised video object segmentation. So the task of semi-supervised video object segmentation is quite popular. So we're given the segmentation of the object of interest in the first frame, and we want to segment that same object throughout the video. So when there's multiple deer, we want to segment this deer of interest throughout the video. If we want to do this in a capsule framework, we can again think of capsules as modeling different entities within the inputs. And we could say routing by agreement, or routing finds agreement between these different entities. So if we leverage both of these ideas, we can use capsule networks for this task. So we once again create a set of capsules from the video. Then we create a set of frame capsules. The video capsules will model different objects within the video, while the frame capsule will model the object of interest in the first frame. And then routing by agreement can find the agreement between these sets of capsules. So here we go. So we have our video, we encode it into some video capsules. We have our reference frame and segmentation. We encode that into frame capsules. And then we pass that through some form of capsule routing to get a set of conditioned video capsules. So these video capsules should represent the object of interest within the entire video. So how do we do this capsule routing? One way would be to simply use the multimodal capsule routing I discussed earlier. That actually does achieve pretty good results, but more can be done applying attention into the routing. So if we can adjust the EM routing algorithm to find the agreement not only between all capsules that are passed in, but rather between two different sets of capsules, right? The video capsules and the frame capsules. And then this should condition the video capsules based on these frame capsules. So I'll go over that now, this attention routing. So we use the same terminology as the transformer networks and attention. So we have a set of value votes, key votes, and query votes. So the video capsules produce, we multiply them by their transformation matrices to produce some value votes and some key votes, and the frame capsules are multiplied by their transformation matrices to get some query votes. So value, key, and query is common in the transformer network, and basically we try to find similarity between the query and the key and perform some sort of softmax extension to get an output from the value. So, so first we get the query votes and we pass it through the EM routing algorithm to get a set of query capsules. Then we try to find the similarity between these query capsules and the key votes. To do that, it's a simple Euclidean distance between these. So we find the Euclidean distance between all the key votes and the query capsules to get our distance matrix. Then, so this distance matrix represents how similar the objects represented by these votes are to the objects represented by these capsules. So a small distance would mean that they're very similar, whereas a large distance means that they're probably different objects. So then these, each row of the distance matrix is passed through a softmax. So the inverse of the distance is the softmax. So this gives us assignment coefficients, which tell our network how much of a lower level capsule from the video will send information to the higher level capsules. So we have our assignment coefficients. So once we have this, we can apply this to the capsule votes in the M step of the EM routing algorithm to get a set of conditioned video capsules. And these conditioned video capsules represent all the object of interest throughout the video. So I'll go over the algorithm now. We're given a set of video capsules, a set of frame capsules, and the different transformation matrices for the value, key, and query. So we get the different value votes, key votes, and query votes. We pass the query capsules, query votes into the EM routing algorithm to the query capsules. We compute the distances between the query and the key. We get the assignment coefficients through the softmax operation. And then we pass that assignment coefficients and the value votes into the M step of the EM algorithm. So at the end, we would have capsules representing the object of interest throughout the video. So we use this attention routing algorithm in the capsule loss architecture. So I'll go over the different parts of this architecture now. So the video encoder, the input consists of 8 frames at 128 by 224 resolution. These frames are passed through 6 2+1D convolutions to obtain some set of feature maps. And then video capsules are obtained using a convolution operation. And we end up with 12 video capsule types. The frame capsules, frame encoder consists, so its input is the first frame as well as the segmentation mask for the object of interest. No? Okay. This is passed through a series of 2D convolutions to get some feature maps, and then it's passed to a conv LSTM. So this conv LSTM helps the frame capsules remember objects when they leave the scene or they're occluded. And we end up with 8 frame capsule types. This is the video capsules and frame capsules are then sent through the attention routing algorithm to get a set of conditioned video capsules. It results in 16 capsule types, and it's a strided operation, so we get this dimension. Then these conditioned video capsules are sent through another capsule convolution. So both of these convolution operations make use of that capsule pooling. If not, this network would never fit into a standard GPU, a single GPU. So it's passed through a secondary convolutional capsule layer, and then these capsules are sent through a decoder network with transposed convolutions. And the output is a segmentation for those 8 frames of video. So as you can see, the spatial dimension of these videos is not that large because we have to fit these into memory, and capsule networks are memory inefficient. So in order to deal with this, we introduce a zooming module. So what this does is, suppose there's a small object within a video. So as you can see, this person is quite far away. If you were to resize this to 128 by 256, the object would be maybe a couple of pixels large, right? It would be quite small, and then any network you pass that segmentation to will lose the object within a couple of frames. Instead of doing this, a zooming module is used to learn to crop a bounding box around the object of interest, so a higher resolution object is passed through the capsule loss network. This allows for better segmentation for small objects. So this zooming module helps for smaller objects. It's a 2D convnet with an LSTM layer, and the output is the bounding box dimensions centered around the object of interest. And these bounding boxes should encompass the object within the future 7 frames, which the network will segment. So capsule loss is trained end-to-end. It uses 2 segmentation losses. So the first is a binary cross entropy, and the second is a dice loss. It makes the zooming module uses an L2 loss to find the height and the width of the bounding box it must produce. And it's trained end-to-end using the sum of these 3 losses. So this network is evaluated on the YouTube VOS dataset, which is a pretty recent dataset. It's the largest video object segmentation dataset that's available, and it achieves state-of-the-art results. And it's also almost twice as fast as other state-of-the-art methods. So here's a speed analysis of it. So basically, capsule VOS achieves 62%. S2S, sequence to sequence, achieves 2% better, but it's about 100 times slower because it uses online learning. So yeah. So here's some qualitative results. So as you can see, the capsule network is able to segment the objects quite well. So in this case, as you can see, even when there's quite a bit of camera motion, it's able to track and segment the object. Okay. And even when there's multiple objects, capsule VOS is able to segment the objects quite well and maintain the boundaries between the objects. So if you look at this example here, there's 5 sheep of interest, quite small, in a flock of sheep, and the network is still able to segment it quite well. Yeah. Here are some other examples. All right. So to see how capsule VOS deals with occlusion and objects leaving the scene, we could test the capsule VOS with and without the memory module. So as you can see, this parachute is segmented correctly, but then it leaves the scene, and then it's unable to be segmented because the network forgets about the object of interest. But the use of the memory module changes this. So once the object leaves the scene, it's able to segment the object successfully. Similarly, in cases of occlusion, right, it's successfully segmented, and then this is occluded for quite a long time. But without the memory module, the object is lost. With the memory module, even after this large occlusion, the frame capsules remember where the object is, and it's able to successfully segment the bear. So here are some video examples. So the bear is occluded by this wood, and then also this woman segmented in pink is occluded by this other woman, and it's segmented even after the occlusion. So we can also see the effects of the zooming module. So for example, this is the first frame of the video. As you can see, the objects of interest, these two people and the ball, are extremely small. So we can test our network with and without the zooming module. So without the zooming module, the capsule network loses or missegments this ball after 20 frames, and then this woman and this ball are lost after 90 frames. But with the zooming module, the capsule network is able to finally segment all objects even after 90 frames. Similarly, with this example, without the zooming module, the segmentation deteriorates over time, and then by the 95th frame, it's completely gone. But with the zooming module, it's successfully segmented. So here are some video results. So as you can see, the spider is quite small, but even its legs are able to be segmented by the capsule network. And even these people who are far away can be successfully segmented. And so in summary, I've shown you the new attention routing algorithm and how it's used in a semi-supervised video object segmentation using capsule networks. And it achieves state-of-the-art results on the YouTube VOS data set. So that's it. Yeah.
I'm Trotting alone. I'm going to be talking about some segmentation and biomedical applications of capsule networks. Basic outline of the presentation is sort of what are the challenges we face that's unique to segmentation. How do we apply capsule networks in this problem domain? And I have a little code demo at the end. You guys can kind of see how this works. Some interesting challenges that we deal with in segmentation is we typically have larger image sizes. We typically don't try and perform segmentation on 28 by 28 pixel images. We're typically dealing with much larger image sizes. And we similarly have a dense output size. Typically we want classifications at every pixel location, or at the worst something like a stride 4 that we then upsample. So we have a dense input, dense output, and that makes it very challenging to fit into memory when you start dealing with segmentation as opposed to classification. Additionally, in segmentation, typically we try to balance global and local information, and this again makes us have to deal with things at very different scales, and dealing with that scale gives us another issue with GPU memory, trying to make these as efficient as possible. So in a work that I published at the Medical Image Deep Learning Conference, it got the CVPR award for that conference. We introduced a couple novelties, one of which being locally constrained dynamic routing. So here we only route child capsules to parent capsules within a given kernel, similar to what we do with a convolutional layer as opposed to a fully connected layer. And this allowed us to dramatically reduce the parameter burden, just like a convolution operation does with CNN. Transformation matrix sharing. In this way, every parent capsule still has a unique transformation, but child capsules share transformation matrices across spatial locations. And so this way, when we're trying to transform, where is the roof of the house, we'll share that feature vector that's trying to transform roof to the parent of house, we'll share that spatially. Same thing we do with convolutional networks, so nothing crazy out there with that. But these two things being added to convolutions help with the memory a lot. Another of which is deconvolutional capsules, so we're the first people to introduce deconvolutional capsules. In this way, the prediction vectors are formed using a deconvolutional or a transposed convolutional operation, and this allowed us to create the classic encoder-decoder network structure that you see very common in segmentation approaches. You can think of like UNet in medical imaging is earlier this year became the most cited paper in the medical imaging, the McKay conference. It was the most cited paper in the history of McKay. So it's a very common structure, very, anyway. So here's the locally constrained dynamic routing algorithm. This is the key line here, where basically, again, all we're doing is we're constraining our prediction vectors to some kernel within the grid, and those are the predictions that we route for each parent is based on this local kernel. Transformation matrix sharing, as I mentioned, in a traditional convolutional capsule when they were first proposed, they used different transformation matrices for every member of the grid as well as for each capsule type. In our work, we restricted this to only be for each capsule type, but we now shared our transformation matrices across members of the grid. Deconvolutional capsules are exactly what you think they are. The prediction vectors are formed using transposed convolutions, and the routing is still performed exactly the same. It's just how we're forming our predictions. And using these, we were able to create a segmentation architecture. Our goal here was to create something as close to the original Sarah Sabur implementation as possible so that we could compare directly with them. And then in our next step, we wanted to kind of push this further. And here we created a deep encoder-decoder sort of UNet style architecture. And these two performed extremely well for the tasks that I'm going to talk about right now. One of which is pathological lung segmentation. You can see on the left, this is a large-scale medical CT scan data set. Has a lot of different pathologies like ground glass opacity, nodules, emphysema, and many other such issues that make segmentation a challenge. The other application that we were looking into was retinal blood vessel segmentation in fluorescent angiogram videos. And here are the results. So this is comparing against the baseline UNet. You can see UNet struggles in areas that have similar Hounsfield unit values or intensity values if you'd like. There's a lot of segmentation leakages and things of that nature. So here's the results. SegCaps was able to outperform UNet by a close margin while only using about 95% fewer parameters than UNet. So that was very exciting to see. And there's actually several works that have come out now specific to medical capsule networks that show that capsule networks tend to require less data for training, at least in the medical domain. That's a trend that we're starting to see emerge. We also looked at the reconstruction of the capsule vectors, and we can see here that different dimensions are in fact capturing different aspects of the image, which was kind of exciting to see. Next application, this is the retinal vessel segmentation. Here you can see on the left, UNet is struggling with under-segmentation on this particular patient. There's a lot of areas where you can see UNet is missing some of the smaller vessels that SegCaps doesn't have that same issue with. And on the right, with a different patient, UNet is having the opposite problem. It's over-segmenting, and you can see a lot of areas of that magenta color in there where UNet is really struggling. And I think I can highlight them for you. Yeah. So you can see areas, especially in here and here, where UNet is really over-segmenting, and SegCaps doesn't have those same issues. Cool. The big thing that everyone's all excited about with capsule networks is obviously the affine transformations. It's equivariant to affine transformations. whereas a traditional convolutional neural network is only equivariant to translation. So here's an example where this was work done by the gentleman right there that is cited on the top of the slide. They train only on a single image, overfit on this image, and then test on different rotations and the mirroring of that. And you can see that the SegCaps is able to do a much better job of segmenting to those novel rotations and viewpoints as opposed to UNet. Another example of a similar vein is X-ray segmentation. So given X-rays that are normally trained straight up and down, this person rotated by 45 degrees, and you can see UNet struggles a lot to be able to handle that rotation that it doesn't see in training. I have a little code demo. You can follow this QR code or the link, and I'll just pull it up really quick. I don't have a ton of time to talk to you guys, but I'll just give you a little preview here. You can go play, load up the data, load up the model here, read in the CT scan and run it through, and you get some output that looks like that. So if you guys want to go, this is in Google Colab. You know, GPUs are all there and everything. You can go play with this. It's public. And when I flip back to my slides, yeah, so you can either go to this link if anyone wants to snag a picture of that, or I'm going to go to the next slide. You can also get to it from my website, from my project page here. Also, the code for all of this is publicly available, so feel free to look at it. There's already been a couple different clones. A gentleman contacted me that it's in PyTorch now, and somebody's also extended it to MS Coco as well. So, cool.
I'm Tolga, and I did this work with a great set of people, actually. I'm quite proud. So this is about shifting this domain. And this is great to talk here because you all had this introduction about the capsule networks and everything. I can just speak about the domain and how this applies and what kind of ideas we talk, right? So we go to 3D data. You have seen 3D data already? That was in video format, right? But video has this temporal component, so it's not actually a spatial axis there. All the frames are kind of correlated with the previous one. However, what happens when an independent axis comes in and this data lifts to true 3D? And this time you have all these representation differences, right? With 3D data doesn't fit into one representation directly, immediately. So some of those are better for certain applications and some others not. So who has worked in 3D and who has worked in 3D deep learning, for instance? Okay, so that's very few. For those, please bear with me a little bit. It will be maybe a little boring, but I will first explain this domain and how we approach it. Okay, there are many different representations, graphs, octrees, implicit surfaces, all those things. And here, we want to do something different. Actually, this is very common. It's not that we invented this, but we want to work with point clouds. So the point clouds is so what's the point cloud? It's basically a set. It's a set, not a matrix, even though this looks like a matrix, of attributes. So that you can have any d-dimensional attribute list associated to a point. Okay? And these attributes define certain things like location in space, the color of the object, differential properties of the object environment. It has many advantages. First of all, it's the raw and generic form of 3D data. Regardless the sensor, it's able to explain the 3D environment. It's just a set of points and this set of colors. That's that pure, right? And therefore it's sparse, so it doesn't fill up the entire room. If you think about it, we actually don't fill up the entire room. So if you want to represent ourselves in this room, you don't want that we store all the empty voxels or the empty space around that's just air, right? So we can go to arbitrary accuracy as well, like, because a point could go up to a floating point accuracy and there's no discretization on it, basically. Well, except the machine precision. Yeah, so though they are hard, of course, because they are now not like features or anything, because these are sets. It's an unordered sequence, and then it represents an unstructured geometry. It's not living in a grid like the 2D images. And then just because they are sets, they are also permutation independent, kind of. And if you take any CNN, that will be permutation dependent, rather. Right, so there is sparsity and there is density variation. So if I have a camera and if I shoot you guys from here, it will be like I have a lot of points in front of the scene here, like the stage, and then less points at the back because of this the angle between the rays, basically, right? So you want to handle all of these things, and there is a particular network designed for this by Charles Chi. And what it does basically, it just accepts the n times 3 point set that is just the locations as input to an MLP that is particularly designed in a permutation invariant way. And it extracts some local features per point and then aggregates those local features with some form of pooling. There could be many methods, of course, to do this. Max pooling would be the simplest choice. Into a global feature, and then you can append any type of loss on it. So I will briefly explain what that is. So we have this input, which is n by 3, and then this goes through what is called an input transformation, which basically is a learned transformation kernel, like spatial transformer kernels, that will take the point cloud, rotate it into a canonical frame, such that our representation doesn't have to care about the rotation of the input. Right? And this is done in a two-level, with a two-level learned kernel. And afterwards, there comes these point-wise one-by-one convolution operators to create rich feature maps. And at the end, we have the max pooling operation that aggregates them to the global feature, right? The latent space. And we can have many loss functions on this, just like a normal CNN would have. Okay, so this is, I would say, the de facto standard right now to process point clouds with deep networks. And on top of this, we want to build a new 3D autoencoder, basically. So of course there are 3D autoencoders, but which is more expressive and maybe more capable of doing other applications, right, that the others didn't have. So we will deal with shapes. Our input is a 3D shape. And we have an encoder, of course, this is an autoencoder, resulting in a latent feature. At this point, I want to say, I will take a different direction in the sense that all these terminology that you know about the capsules, that will apply here, but we will see it from a different perspective. First, because it's a new domain, and second, different properties of the capsule networks will help us to do different things. Right? So the decoder, of course, and there's a reconstruction, and we will be measuring some kind of a reconstruction loss, of course, and in 3D that's usually the chamfer distance. So now comes the latent capsules, right? Now we see them as multiple latent vectors that we can play with. It gives you the ability to, once we have all these vectors or all these capsules, we can do different things with them. Pose is obviously one of those. However, there could be other things. And we won't focus on pose, actually. So what happens if you have multiple latent vectors, right? This is actually great. This is actually something that the other CNNs just don't give you. And it's different than having one single latent vector, one single long latent vector, just because, there is this capsule idea and the routing and clustering on top of it. So what we can do, we can, for instance, take different capsules and make them specific to certain parts or anything, right? And we will actually observe that these capsules, when processed that way, just, the architecture is just the same as a capsule network, maybe, with the modification that the encoder is a point net, and decoder, I will explain how we can achieve different decoders for point sets in a short while. So we see that these capsules, actually what we can decode from them, they specialize into certain regions already without any supervision, right? So these are all the points that the capsules get localized to. They are just really reconstructing those parts. And, right, so I will come back to this in a second. And how we can formulate a decoder? How can we actually upsample a point set, right? Normally, if you have a 2D image, you would just memorize the locations of the max pooled feature maps and then use that during decoding, for instance, or you know, any other deconvolution operation and so on. In 3D, especially for point clouds, where the input is unstructured, yet the output is also unstructured, this wouldn't hold anymore. So it's very hard to invent some points in 3D space. You know, you have to bring them from somewhere. There are many efforts, but I think a more principled approach, at least for objects, is this one. So instead of trying to make up points in 3D space, we think of this object as a two-manifold, where you know, where it can always be unwrapped to a sphere or to a plane, right? And the idea is that if I take my napkin now, you know, some like a sheet, and wrap it around the object, so wrap that sheet around the microphone, and instead of learning to make up points, I could learn the function of deformation. I could learn the parameterizations. So that's the basic idea that these guys called folding net came up with. Simultaneously, AtlasNet also came up with it, but yeah. So that's how we make a decoder for point sets, right? And now we look at different decoders. I'm not sure if you can see. Yes, you can. So what happens is in all of them, so basically this guy, this fixed grid, right? This thing is just a 2D plane. So this is sampled points on some 2D space, and then we have this global code, and this grid kind of combines with the global feature vector to deform on top of the output, on top of the object that I want to reconstruct. So different decoders exist. And what they do is, the simplest one, of course, doesn't have the grid. It just has the latent vector and decodes or reconstructs the output from that. It's quite hard. And then there is this folding net that just uses one set of grids to decode an entire point set. Well, that is somehow limiting, of course. And then comes AtlasNet, that basically takes a feature vector and then multiple grids. You can think of it like multiple patches surrounding the object. So I have these multiple napkins now, and I'm wrapping them around different parts of this object, right? And of course, this is more capable of, it's richer and results in better reconstructions. What they don't have though now, they are all limited to this single dimensional latent vector that we cannot really use, right? I mean, I cannot really control this vector to the parameters of the shape. I cannot instantiate it as in the capsule. So now we can have these multiple feature vectors. Right? That is really good, and we can see what happens in a second. So let me briefly give you the architecture. So we have a point cloud n by 3. We have a neural network that processes it as raw, it consumes it raw completely, and then of course results in some feature maps. Right? These convolutions are again on top of the points. There is no neighborhood because we are also permutation invariant. So from that, now you know, branch this feature map off to create these to result these different capsules, and each of these feature maps in themselves get this aggregation. Now we form this primary point capsules, which is a concatenation of all these things. Now comes the dynamic routing that routes these primary point capsules to the latent capsules that I actually want to have. Right? And just like the original capsule networks, we will have a decoder right there. But now we will have this idea of folding a napkin for each capsule. So we take these capsules and then append different grids on top of these capsule maps. And then so combination of each one of them basically results in certain reconstruction of the object because of the decoding. So remember, we learned the deformation function. We don't invent points, right? So we just deform these grids on top of the 3D. And that is just learned by some MLPs. That's what deforms the grid. Okay, and then we end up with this reconstruction, and we see immediately that the same color represents the same capsule. Okay, that we see that they don't just distribute across space. They choose certain regions of space to reconstruct, right? And that is, well, there's multiple reasons. Primarily, I mean, we have the routing procedure there. You know, that's kind of a clustering already. Plus, these decoders are, so that is also an argument going on, it's debatable, but I would like to give it to you, is that they choose the easy things to reconstruct. So if I'm basically spreading out these reconstructed point across space, that is basically I am deforming my napkin too much. However, the network or any optimization algorithm will converge to something that actually doesn't move it that much, doesn't want to move it that much. So why keep them distributed, whereas I can keep them local? So of course, this immediately calls for part segmentation, right? Because now we have already these things across different parts. And what happens if I supervise this thing now? So I will just take a part segmentation data set, so some data set where the objects are labeled with parts, and then I will make my capsules specific to those parts. And I will just, hey, this green thing that is over there, I have the input label for it, right? And then I will just sample the part labels for it and associate. And that's it. And I can do this for multiple capsules coming from, the same parts, or multiple capsules can come from the same part. And then I can just do my predictions, right, after some layers. And of course, there will be some loss to classify them. It's a supervised thing in the end. And I can now do the part segmentation, because from the latent space, I can go to these part predictions, right? And then I can also know, I also know the association to the latent capsules. So I decode that is possible. Therefore, I end up with these part segmentations, which look like those. And it's pretty close to the ground truth. So I don't have much time. Therefore, I will not pause on them too much. But they are actually good. And then we can do other applications now, because we have a rich latent space, right? It's not like typical features. So what we can do, we can take a source shape, encode it, get its parts, right? And then we can take a target shape, encode it, get its parts, right? And now we know the association between the wings, because the wings now, we have them in the latent space, we can control them. So if I just switch the capsules for the wings, I'm actually ending up with two planes, the parts are flipped in a consistent and globally coherent way indeed. And that looks like that. So it's really fine in that sense. Right. More examples. Actually, I would skip that, but I would show you this. So the interpolation is also smooth without any add-on loss on this, right? It's really just, we are interpolating the latent space only. And you see the topology, of the two legs of the table, they come together, so it can also handle topology changes. We apply it to 3D feature extraction, get the state-of-the-art results, of course. We also do other things. We do multiple applications now with this, right? We just take any application where the point clouds are used in an autoencoder and just apply our thing. And the results are actually really good. So, thank you for listening. And I just have a couple of take-home messages. I think the input representation is quite important for applications, plus how we parameterize our latent space, how we impose a structure, on our bottleneck features is actually important. Right? We want to make it rich, we want to make it structured, maybe with some geometry, with some meaning. That's important. And now we are working on specializing capsules on other things, like 3D pose, deformation, whatnot, you can imagine. So the code is available, you can play with it. And I thank all my collaborators for this. For me, it was very enjoyable. Thanks a lot.
Good afternoon, everybody. I'm Marzieh, and in this last section of tutorial, I'll be presenting subspace capsules. Let's start with the definition of capsule. By definition, a capsule is a group of neurons that encapsulate the probability of presence of an entity and also instantiation parameters of the same entity. While a capsule can be represented in different ways, like we can represent it using a matrix, here we are interested in special case that we represent a capsule using a vector. Then we follow the principle of separating the probability of presence of an entity from its instantiation parameters. And we use the capsule length to show our confidence level in detecting the presence of an entity. Here, as you can see, the capsule corresponds to the sample boat is large, while the deformed sample has a small capsule vector. Then we use the capsule vector orientation to encode instantiation parameter of the entity. These instantiation parameters are, for instance, different colors can be represented using different orientation in the capsule vector, or different viewpoint, or different lighting condition. Here now we want to introduce the subspace capsules. In subspace capsule, we share the idea of representing a capsule using a vector. We also follow the principle of capsule network, and we use the capsule length to show the score of presence of an object and also encode its properties in capsule orientation. But what is different here is that we do not simply group neurons to create a capsule. What we do in subspace capsule is that we model the variation in the appearance of an entity using a capsule subspace. Then each sample can be represented using a vector in this subspace. So as you can see here, each sample is a vector in the learned subspace. When these capsule subspaces are learned, we can create the actual capsule vector by finding the degree of alignment between the feature of that sample and the capsule subspace using a learned transformation. As you can see here, we have a subspace for class car, and this is the feature that extracted from this sample, and the actual capsule corresponding to this sample can be created by projecting this feature vector onto this subspace. Now we can introduce CapProNet, which actually use the idea of subspace capsule in supervised image classification. This is a joint work with my colleague Li Heng and Dr. Gu Junqi. So basically, in CapProNet, we learn a group of capsule subspaces to represent a set of entity classes instead of just grouping neurons. So consider here the classification problem that has L classes. In CapProNet, we learn L different capsule subspaces and model the variation in properties of each class in one capsule subspace. So here for class boat, we learn one subspace, and so on and so forth, till the last class that we have another subspace for class car. When capsule subspaces are learned, then we create the capsule vector by orthogonally projecting the input feature vector onto the capsule subspace. Here we have the capsule subspace for class both, and this is the extracted feature from that, and the corresponding capsule vector for that, V, is generated by orthogonally projecting this feature vector onto subspace. So in a well-trained CapProNet, we expect that if we have a capsule subspace for, let's say, class both here, subspace capsule vectors correspond to both samples, like this vector x1, to be larger than samples of all other classes. And we can also use orientation of these capsules to represent different properties of input samples. So here we can see that two samples from the same class both have different orientation that, for example, different orientation can encode different properties of them, like different viewpoints. Now let's see how a CapProNet model architecture looks in general. We have a labeled training data. X is sample, Y is the corresponding target. And we pass samples through a backbone CNN architecture. We get a feature vector X, which is a d-dimensional vector. And then we learn a group of capsule subspaces S1 to SL such that the norm of the capsule vector correspond to the target class be larger than all other classes. Now that we got the idea of CapProNet, let's formalize this idea. For each capsule subspace S, we learn a weight matrix W, which has the shape of D by C, which D is the dimension of input feature vector and C is the dimension of subspace. So basically the subspace is defined by the span of the columns of this weight matrix W. Then, to find the actual capsule vector, we need to find a vector V on this subspace such that the distance between the feature vector X and that capsule vector is minimum. So this minimization problem has a closed form solution, and we can actually find the capsule vector V by applying the projection matrix here, which has been defined like this. So basically P is the matrix of orthogonal projection onto subspace. And since we need norm of capsule as our confidence level about the presence of the entity, we can find the norm simply by Euclidean norm can be defined by square root of V transpose V, and using some mechanical operation and substitution, we get to this final formula, which sigma here is basically W transpose W inverse, and we, for simplicity, we defined it as sigma. Now let's see how we train the CapProNet. Given a group of capsule vectors, V1 to VL correspond to a feature vector X, and ground truth label Y, we want to train this CapProNet such that the corresponding capsule vector Vy to have larger and greater value than all other classes. We can train this model using standard loss function, for instance, by minimizing the negative log likelihood loss. And yeah, okay. We talked about that. We learned some capsule subspaces and how we create the actual capsules. Now we want to see how these subspaces are actually learned. To do that, we need to analyze the gradient of loss function with respect to bases of these subspaces. Consider here that we have a subspace S, and it is defined by the two bases, W1 and W2. And we have this feature vector X, and the corresponding capsule on this subspace is VL. This X perpendicular is actually containing novel characteristic of this sample that this subspace cannot represent yet. So we want to take the gradient of this loss function with respect to basis of this subspace. Using the chain rule, we'll get to this formulation. Despite its daunting look, there is a main point in this formula, and the point is, in this gradient, we only have columns that are parallel to this X perpendicular. What does that mean? It means that in each iteration, bases of these subspaces, W1 and W2, only get updated in the directions of these two red arrows. And it means that we're actually tilting the subspace in a way that the norm of the subspace capsule would become larger for the target class. Now, this iterative process actually continues till this feature vector can be fully contained in the subspace, or misclassification error is very small. We evaluated the performance of this model on different datasets, on CVPR10 and CVPR100, on Street View House number dataset, and also on ImageNet dataset. As our backbone structure, we use ResNet model and DenseNet model. And what we did is that we take the backbone structure and replace the last layer of that with CapPro layer. This is the result we have based on the ResNet backbone and with different capsule subspace dimensionality for different Cs. As you can see, both for original ResNet and ResNet with pre-activation structure, regardless of the capsule size, we got better performance than the baseline. We also evaluated based on the white ResNet structure, which has the similar structure as ResNet, but it has more feature maps in residual blocks. To summarize these experiments, CapProNet with ResNet backbone actually reduced error rate by 19% for CVPR10, 17.5% for CVPR100, and 10% for SVHN dataset. And to make sure that the improvement that we get is independent from the backbone structure, we also repeat experiment with DenseNet backbone for all datasets. And for DenseNet backbone, we also got improvement over the baseline, which is 5.8% for CVPR10, 4.8 for CVPR100, and 6.8 for SVHN dataset. We also compared the result with the CapsNet model And as you can see, in regard of parameters, the CapProNet with DenseNet backbone has much fewer parameters compared to CapsNet, original CapsNet, while it has significant improvement over the actual Capsule network. We also have results for SVHN dataset with almost similar number of parameters. Again, CapProNet with DenseNet backbone achieved better result than the baseline. And to test this scalability of CapProNet, we also tested on ImageNet dataset using two ResNet backbone and with different subspace capsule dimensionality, and we achieved an average 3.5 to 4% improvement over the baseline. We also evaluated the effect of capsule projection. For this experiment, what we did is that instead of orthogonally projecting, we take the W matrix and we create a capsule of C-dimensional directly by transforming this feature vector onto data space, and compare the result with the actual CapPro layer. As you can see here, we can see that orthogonal projection plays a significant role in improving the performance of this model. We also visualize the projection onto capsule subspaces. Here, we have samples for one class of CFAR 10 dataset, and in two-dimensional space, and red samples represent, red dot represents samples that belongs to this subspace, and green dot represents samples that belongs to other classes. As you can see here, samples that belong to this class has larger capsule lengths relative to origin in compared to those samples that does not belong to the class. This is the visualization that we have for all 10 classes. As you can see, in all of classes, we have the same result, that samples that belongs to that class has larger capsule lengths compared to samples that does not belong to that class. So to recap what we presented a null subspace capsule projection network, and which learns a group of capsule subspaces for different classes. The model improves the performance of backbone architecture without incurring large computation or memory overhead. Actually, we don't need any routing in this model. And the improvement achieved by applying capsule projection on the last layer. Now we want to introduce subspace capsule network. Basically, the idea is that, okay, capsule projection, orthogonal projection is good, but we only applied it on the last layer. So can we make it more general and apply it in other layers as well? There's a challenge here. So CNN highly benefits from various number of feature maps and also different receptor field size. But orthogonal projection matrix restricts the output size of the capsule. So basically, when we use orthogonal projection matrix as defined here, the output capsule would have the same dimensionality as the input feature vector. So based on orthogonal projection, Capsule Pro layer keeps the dimension of capsule vector fixed. To deal with challenge, we need to find a transformation that led us to move between different dimensionality of space. And we also need to find a transformation that keeps the degree of alignment between the input and the capsule subspace. So here, if we create a capsule by orthogonal projection matrix P, we need to find the transformation, let's say PC, such that the norm of the capsule in both transformations are preserved. And finally, we need to preserve the relation among vectors on the capsule subspace. So here, if we create a capsule V1 for this feature X1, and we have another capsule V2 for feature X2, we want that the angle between V1 and V2 to be the same as the angle between the corresponding capsules that we create using PC transformation. It can be proved that if we decompose the orthogonal projection matrix P as follows to PD multiplied by PC, and these two are defined here, and use transformation PC instead of orthogonal transformation, we can satisfy all three requirements that we mentioned. So we can move between different dimensionality of a space, we can preserve the norm of the capsule vector, and also we can keep the relation between the capsule vectors. We also extend the idea and to bring in the idea of weight sharing in the convolution in the subspace capsules. So here, if we want to create a kernel that has k by k receptive field, and we want to create a capsule subspace that has c-dimensional space, we need to have a weight matrix that belongs to this space. So, and we can create PC, the transformation that we need, based on this formulation. Now, all we need to do is that we need to reorganize PC matrix to a convolution kernel with the shape of C, I, and K by K. And now, if we convolve this kernel on input feature vectors, the corresponding capsule would be placed along the output feature maps. We also have two different activation functions here. The first one is based on the probabilistic view. When we want to see the norm of the vector as the probability of presence of an entity. So in this case, we use the squashing activation function, which is similar to the original capsule network. The other perspective is that the scoring view, which basically we are encouraging a capsule to have at least a minimum length B to get fired. So here, this B is the threshold that if the capsule is not larger than that, we turn the capsule completely off. We evaluated this idea on generative adversarial network, and I believe that most of you knows about this framework. It consists of two networks, generator and discriminator, and we applied it, except then generating samples, GANs can be used in semi-supervised classification tasks. So what we did is that we replaced the discriminator of the GAN framework with subspace capsule network. And we applied it on classification for two different data sets, namely CVPR10 and SVHM. This is the architecture of the discriminator that we used in our experiment. The generator is basically the same as the architecture that was used in paper-improved technique for training GAN, but in discriminator we have a couple of convolutional layers, and we replaced the last 4 layers of discriminator with subspace capsule layers. For classification on CVPR10 dataset using only 4,000 labeled samples, we achieved 20% improvement over our baseline, which is basically improved GAN. We also have result for SVHM dataset, which we use only 1,000 samples, labeled samples, and we also got 43% improvement over the baseline. We also use the idea of a subspace capsule network in image generation tasks for a couple of data sets. For MNIST, Celeb-A, and ELSON dataset, and what we did is that we replaced the regular generators with subspace capsule networks. For the experiment that we did for MNIST dataset, our goal is to see that whether the subspace capsules in the first layer can actually model different properties of the output generated image. The architecture is like this. We get the latent representation Z and we project it onto 10 different capsule subspaces. We take the one that has the largest capsule vector and we project it back to the actual subspace dimensionality. And then we have a couple of upsampling and subspace convolution layers. And the final layer is basically the regular transpose convolution. Here we have generated samples for MNIST dataset, and what we did here is that we take the capsules of the first layer and we tweaked one dimension of that in the range of -2.5 and 2.5. By tweaking different dimensions, as we can see, we can generate samples that have different properties. Here, by changing one dimension, we change the rotation in the generated samples. For another dimension, we have localized part, and we have scale, we have translation, thickness of a stroke, and thickness plus scale in these samples. And finally, localized screw can clearly change here when we tweak the one of dimensions. We also applied subspace capsule network in generating high resolution images for ELSON, bedroom, and Celeb-A dataset with resolution of 128 by 128. We have in our discriminator the same architecture as progressive growing GAN, but in our generator we replaced the first 4 resolution with subspace capsule layers. And here we have a squashing activation function for our generator. Here is the generated samples for ELSON bedroom dataset. As you can see, we achieved significant improvement in FID score over our baseline. This is samples for Celeb-A dataset. Again, we have improvement for FID score, and generated samples look really natural. We also move forward and try to generate samples for higher resolution of 256 by 256 for ELSON CAT and ELSON horse datasets. In these experiments, we replaced all of the layers of our generator. We updated them to subspace capsule layers. This is the generated samples for the ELSON CAT dataset, and we improved FID score of the baseline significantly, reducing it from 37.55 to 29.19. We also have generated samples for horses, and to make sure that our model doesn't memorize samples, we actually did the interpolation in the latent space by generating by taking two latent vectors and interpolating between them and generating samples for the interpolation. As you can see here, we have samples, and the transition between these samples is smooth, and the generated samples have high quality. And this is more simple. We also did the same experiment for horse data set, and as you can see again, we have a smooth transition in latent space. We also have latent representation, interpolation and latent representation for bedroom and celeb A data set. And to summarize what we presented, subspace capsule networks are based on learned transformation. So capsules are generated by projection onto capsule subspaces. We don't need any routing in this model. And during the test time, actually computational time is the same as regular CNNs. So we don't have any time overhead. And subspace capsule network can be applied on both discriminative models and generative models. And this is a reference of our work, and thank you.